Okay, welcome to the 5.1 video. I apologize, I did not put a namespace at the top of this page. So if you do disconnect the kind of formulas and review page from the 5.1 page, please make sure to put your name at the top. I'll put a little thing here, so kind of as a reminder. If you're keeping them stapled together, it doesn't really matter that way. If they get lost, I can get it back to you. We're going to start out with some vocabulary. So hopefully you read the chapter 5 kind of introduction summary. We're taking trigonometry and going one step further. We're looking at applications through identities and proofs. We're using trigonometry to do more analytical math. So this is going to get pretty theoretical with variables and kind of understanding things through logic and proof-based examples. So we're going to start out with our first vocabulary word, which is identity. Throughout the entire chapter, we're going to abbreviate identity with just ID. So we're going to start out with some fundamental identities. And an identity is any statement, a statement that is true for any valid input for an equation. So essentially, as long as it's not undefined, then the value will hold true no matter what you input. So if it's undefined on one side, it should be undefined on the other, that type of a thing. So I can put in any, for example, an angle. If we're talking about trigonometric identities, I can put in any angle and I'll get the same value on either side of the equation. So this valid input brings us to the idea that some inputs are not valid. So we want to recall that domain is all possible input values or X values. And that means not those that are undefined. So then the domain of validity is the same thing, but for two different expressions. So if it's in the domain of the right side and the left side, then it's in the domain of validity. So we say all values that are in the domain of both sides of an identity. Okay, so we're going to start out with some identities that we've already seen. So I'm going to go ahead and switch over to our kind of the back page, the identities I'll show you in a second. This one. So it's on the back of the chapter 5 introduction. So the identities to know by memory, we're going to start with our reciprocal identities. Those are the functions that are reciprocals. So for example, the sine of x is the reciprocal of cosecant of x. Cosecant of x is then the reciprocal of sine of x. We also have cosine is the reciprocal of secant, which means that secant is the reciprocal of cosine. And we have that tangent is the reciprocal of cotangent, which means that cotangent is the reciprocal of tangent. So those are all of our reciprocal identities. We've seen these, we've been using these. Our other identities that we've already been using are the quotient identities. So that's that tangent of x is going to be sine over cosine, which we saw as y over x, and then we extrapolated that in the last chapter to mean that it could be sine over cosine. And then by the same idea, we have that cotangent can be written as cosine over sine. Okay, now when I read these functions, I'm not always saying of x or of theta, for example. When I say sine, it's already given that it must have an argument. We're never going to see sine by itself without something that we're taking sine of. So just like with logs and exponential functions and square roots, there's always an argument. There's something that I'm taking sine of. Having sine by itself is the function name, but in itself, that is not a function. Okay, so now we're going to switch back to the 5.1 page. So in order to find our next identities, we're gonna kind of do a thought back to where we originally got sine and cosine from. So the first time we saw this might have been geometry, but we kind of reviewed this in chapter 4 as well. Sine and cosine come from the unit circle. So we're gonna put our unit circle here. And if we create a triangle like this, we can say any right triangle where we have a given angle theta has an opposite, that's a y value, and an adjacent, that's an x value. And specifically for the unit circle, this one is sine, and this one is cosine. And so by the Pythagorean theorem, I know that these are my legs and this is my hypotenuse. So I can say that sine squared plus cosine squared equals 1 squared. And to simplify this, there's really only one part that I can simplify, and that's the 1 squared. So this becomes our Pythagorean identity. Sine of theta, or sine squared of theta plus cosine squared of theta is 1. Now, it doesn't really matter which one comes first, but just out of habit, we usually say sine before cosine. So we say sine squared plus cosine squared. If it flows better for you for cosine squared plus sine squared is 1, that is absolutely fine and will work every time. Our next identity comes from taking that one. I'm going to rewrite it here and dividing everything by sine squared of theta. Sine over sine, or sine squared over sine squared, still gives me 1 plus cosine squared over sine squared equals 1 over sine squared. Cosine over sine is cotangent, so this gives me 1 plus cotangent squared theta equals 1 over sine is cosecant squared theta. And then we have the same thing, but instead we're going to divide by cosine squared theta. So we get sine over cosine squared plus 1 equals 1 over cosine squared. Simplifying that, sine squared over cosine squared is tangent squared plus 1 is secant squared. So we have 3 Pythagorean identities. We can, for the purposes of note taking, call them number 1, 2, and 3. We have our primary one and our 2 that we get from that, and all 3 are useful for us. So we're going to go ahead and copy those over onto our formula sheet. Okay, so I have them written down here in the Pythagorean identities section. Now, the first one really is our primary, and that's the one that we will use most often. And then number 2 and 3, we're calling them number 2 and 3, just so you'll know which one I'm talking about. However, every textbook will have them in a different order, and some of them won't use them as primary identities, and you'll derive them every time you use them and only use the first one. So number 2 and number 3 are not like if you talk to another math teacher or a student from another course or another school, they're not going to say Pythagorean identity number 2 and Pythagorean identity number 3. That's just for us. All right, back to the notes page. In this example, we want to find sine and cosine if tangent is 5 and cosine is positive. Well, we know that tangent is 5, so that's positive, and cosine is positive. If those are both positive, then we must be in quadrant 1. So if we're in quadrant 1, sine and cosine should both be positive, and I know tangent, I could write it as 5 over 1, for example. Tangent is opposite over adjacent. And so I'm going to start with a triangle. Here's theta, opposite, adjacent. To find this one, I need the square root of 5 squared plus 1 squared is the square root of 26. And so sine, is 5 over the square root of 26. We don't have to rationalize, but we could. Then it would be 5 root 26 over 26. Either of those is completely fine. Cosine, ca 1 over root 26, or we can say square root of 26 over 26. Simple as that. The next identities that we're going to look at come from the word co. So we've got sine and cosine, secant and cosecant, tangent and cotangent. Why do we have co for all of those? Well, co actually stands for complement. Complement is two angles that add up to 90 degrees. And if we're looking at a right triangle, the angles that are not the right angles are going to add up to 90 degrees. And so we can see from this relationship that the opposite and adjacent will switch roles. And so we actually end up with a relationship that sine of angle A is going to be equal to cosine of angle B. So I'm going to show that to you. Let's look at angle A first. Angle A, sine, so opposite over adjacent, that's y over r. Tangent, TOA, y over x. Cosine, ca, is x over r. Secant is a reciprocal of cosine, so that's r over x. Cotangent, x over y, cosecant, r over y. Angle B, that's this one up here, we're going to do the same thing. Go ahead and fill these in and then check your answers. So this is what they should look like. Notice that sine of angle A here is equal to cosine of the complementary angle. And when we say complementary, we're saying they add up to 90 degrees. In radians, that means they add up to pi over 2. So if I call angle A theta, then angle B is going to be pi over 2 minus theta. Okay, so when we're looking at sine of theta equals cosine of pi over 2 minus theta, and vice versa. So we get the cofunction identities. Switching over to our identities cheat sheet. Okay, so we're filling in our cofunction identities, keeping in mind that theta and pi over 2 minus theta are complementary, meaning they add up to 90 degrees or they add up to pi over 2. So we can say then that sine of theta, I'm going to use x just because it's a little easier to write. Sine of x is cosine of pi over 2 minus x. I'll put here x and pi over 2 minus x are complementary. So that means I can also say that cosine of x is sine of pi over 2 minus x. We're going to do that for each of these. So we've got sine and cosine. We can do it for secant and cosecant. And tangent to cotangent. Oops, cotangent. Now we're going to switch back to the 5.1 notes page. Hopefully you're not getting whiplash. Our next set of identities come from the properties of odd and even functions. Now, if you did the review packets, you'll remember that odd and even functions come from symmetry. So let's look at even functions. Even, like x squared, 2 is an even number. X squared is a parabola that has symmetry over the y-axis. So this is y-axis symmetry, which means kind of like a butterfly, you can fold it in half. Odd, like x cubed, because 3 is an odd number, has not reflection symmetry, but rotation symmetry. This looks the same if I turn it upside down. So this is odd, has a rotation 180 degrees or pi radians about 0, 0, which is the origin. Okay, so what that means is if we look at all of our functions, if we look at the graphs of all of our functions, let's look, for example, cosine looks like a mustache. What type of symmetry does that have? Cosine has even symmetry, is even, and that means its reciprocal will be even as well. Sine looks like this. What type of symmetry does that have? Sine is odd. And tangent looks like this. What type of symmetry does that have? Tangent is odd. The function and its reciprocal have the same symmetry. So the property of an even function is that if we call this x and this negative x, then their y values are equal. So f of negative x equals f of x. For odd functions, let's call this x and we'll call this negative x. Then f of x and f of negative x are opposites, right? One is positive, one is negative. So we can say f of negative x is the opposite of f of x. Whoops, extra parentheses. That's how we're going to get our identities for our odd and even trigonometric identities. So switching back over to our identities page, we see that cosine was even. So cosine of negative x is the same as cosine of x, and same with its reciprocal. Secant of negative x is secant of x. The other ones were odd, so this was even. Our other ones are odd, so that means sine of negative x is negative sine of x. Cosecant of negative x is negative cosecant of x. Tangent of negative x, negative tangent of x. And cotangent of negative x is negative cotangent of x. So in these ones, the negative disappears. Sorry if I spelled that wrong. For odd, the negative becomes a coefficient. Okay, that's our last identity for today. So now we're going to go ahead and apply it. So in this one, we are given a value for sine, or sorry, we're given a value for cosine, and we want to find sine of theta minus pi over 2. Now that's pretty close to our complementary angle, but it's backwards, right? So the first thing we have to do is rewrite this as sine of negative pi over 2 minus theta. So I factored out a negative. Okay, so all I did is I factored out, so that's negative theta plus pi over 2, but I put the positive one first. So this is our complement. We couldn't use an identity right away because this was not our complementary angle. Now we're going to use the fact that sine is odd. So we're going to write this as negative sine of pi over 2 minus theta. So that was odd. And now we know that sine of pi over 2 minus theta is cosine of theta. So this is negative 0.34. And that was by cofunction. Okay, slight change in background, but we are working on the very last page of the notes. This is applying those identities that we've been looking at. So in example 4, what we're going to look at is trying to factor and simplify as much as possible. And our goal is to just get an answer that's a single trigonometric function. So for example, sine of x or cosine of x or tangent of x, or maybe even sometimes something like cosecant squared of x, something like that. So something simple with only one trigonometric function in it. And the way we're going to do that is we're going to look at this and say, how can I simplify that? And if I'm looking at this, I'm going to say both terms have a sign. So I'm going to go ahead and factor out sine of x. Sine of x times what I'm left with here, sine squared x plus cosine squared x. And hopefully you can recognize that as our Pythagorean identity. So what does that equal? This is the left side. The right side of our identity is 1. So that means sine squared x plus cosine squared x equals 1. So this becomes sine of x times 1, which is just sine of x. I'm going to do here, we did this by factoring, by Pythagorean identity number 1, and then by simplifying. So that when you look back at these notes, you can say, how did I get to that next step? Okay. In the next example, we're going to do the same thing. We're going to say, how can I simplify this? In order to simplify this, the first thing I'm going to do, I notice that these are conjugates, meaning when I multiply them together, the middle term will cancel out. This is secant plus 1 and secant minus 1. So when I multiply those out, it's going to be secant squared x minus 1 over sine squared x. Well, anytime we have a 1, that's kind of a hint that we're going to use one of our Pythagorean identities. In this case, the Pythagorean identity that uses secant is our Pythagorean identity number 3. So first I'm going to say this was by distributing. And then I'm going to say, which Pythagorean identity am I going to use? I'm going to use Pythagorean identity number 3. Now I'm going to write that here as a reminder. Tangent squared x plus 1 equals secant squared x. On our sheet, we used theta, but in here, our variable is x. If I subtract 1 from both sides, that tells me that tangent squared is equal to secant squared minus 1. So I can replace my numerator with tangent squared x. And that is still Pythagorean identity number 3, just slightly modified. So this becomes tangent squared x over sine squared x by Pythagorean ID number 3. Now I've got tangent and sine. Well, tangent I know is sine over cosine, so I'm going to rewrite this as sine squared x over cosine squared x times 1 over sine squared x. Simplify that. That is a quotient ID. And now I'm left with 1 over cosine squared x, which is equal to secant squared x. And that is by simplify and reciprocal ID. Okay. In number 6, I have cosine over 1 minus sine, sine over cosine. There's not really anything I see to do here that I could simplify, but if you remember in example 5, we were able to simplify by multiplying by the conjugate. So that's what we're going to do here. I'm actually going to multiply the first fraction by 1 plus sine of x. So I have cosine times 1 plus sine divided by 1 minus sine squared x. And that happens because they're conjugates, minus sine of x over cosine of x. So this was multiply by 1 over 1 plus sine of x because conjugate. Okay, now 1 minus sine squared x should look familiar. Again, there's a 1 and a squared. That is actually our first Pythagorean identity, but subtracting sine from both sides. So that is sine squared plus cosine squared equals 1. So then cosine squared is 1 minus sine squared. So I can replace that with a cosine squared. Cosine of x times 1 plus sine of x divided by cosine squared x minus sine of x over cosine of x. That was Pythag ID number 1. Simplifying here, I get 1 plus sine of x over cosine of x minus sine of x over cosine of x. By simplify, specifically cosine over cosine is what I simplified in the first term. These now have a common denominator. So I have 1 plus sine of x minus sine of x over cosine of x, which is 1 over cosine of x, which is secant of x. That was simplify and reciprocal ID. Reciprocal ID. Okay, so I have some tips here. Sometimes it helps to rewrite them as sine and cosine. Usually we'll be looking for if there are any common factors. Sometimes we'll need a common denominator, and to get that common denominator, we might need to use a conjugate. We didn't see this example, but sometimes there'll be a fraction and it helps to separate the fractions in order to simplify it. So we can separate, if there's multiple terms in the numerator, separated them out over a common denominator, and then maybe turning that into different functions, combining them into sine and cosine, things like that. So it's really a creative endeavor to simplify these fractions, okay? Or these expressions rather. And you're gonna be putting those identities, that's why I gave you a cheat sheet with all the identities on one page, so that it'll be easy to reference. But the goal is that yes, you can use them to reference, but eventually you want to be comfortable enough remembering them without referencing them, okay? On our last example here, this is similar to the extra credit if you saw it, where we want to solve this. So actually we're going to get values of x, and x here are angles, right? Input of a trig function is an angle. So the difference here is that we're working with equations instead of expressions. If we look back at the top of the page, these ones are expressions, no equal sign. So now what we're looking at is we want all of the values of x in the interval from 0 to 2 pi. So that's one rotation of the unit circle. And we want to solve this. Now the trick here is just like when we were working with rational functions, we want to be careful of undefined values. Anytime we have a denominator with a variable in it, we should take note. So right away, I'm going to say that sine of x cannot be 0. Otherwise, that would be undefined. Then I'm going to simplify this. So I've got cosine cubed x over sine of x equals cotangent x. I just rewrote it. I'm going to go ahead and rewrite cotangent in terms of sine and cosine. That's tip number 1. Cosine cubed x over sine of x equals cotangent is cosine over sine. And then I'm going to subtract it over. Now we want to be careful about multiplying or dividing both sides of the equation by the same thing, because we cannot multiply or divide by 0 on the same on both sides of an equation. So factoring is going to be a much safer way to go. So here I'm going to do cosine cubed x over sine of x minus cosine over sine is 0. I'm going to keep going. Factor out a cosine over sine. Now, could I do this if it was still in cotangent form? Absolutely, I could, but it might be harder to see. And that's why it's sometimes nice to write them all in sine and cosine. So here we're left with a cosine squared x minus 1. That should make you think of the Pythagorean identity. So I'm going to write it here on the sign. Sine squared plus cosine squared is 1. Now I want a cosine minus 1. So now I subtract 1 from both sides. Sine squared plus cosine squared minus 1, but then I want cosine without sine, so I'll subtract sine. Cosine squared minus 1 is negative sine squared. So I'm going to replace that here with negative sine squared. Cosine over sine times negative sine squared is 0. Whoops, equals 0. So now I have, this is cotangent of x is 0. And sine squared x is 0. Using the 0 product property, I want to find each of these. Now we know that cotangent of x is 0 where cosine is 0, right? We need to find places where sine of x is not 0. So cotangent of x is 0 where cosine is 0, which is going to be at pi over 2 and 3 pi over 2. Sine of x is 0, but it cannot be 0, so this is extraneous. I don't have to worry about coterminal angles because it says specifically to find only between 0 and 2 pi. So my answer is pi over 2 and 3 pi over 2. And that's it for this section.